Today the topic for discussion is residue class module N. For A belongs to Z, the set A bar such that X belongs to Z such that X is congruent to A module N is called congruence class of A of module N, or residue class of A module N. So what is the definition of residue class? The notation for residue class or congruence class of the element A. A is the element of Z. You know that this congruence relation is what? Is an equivalence relation on Z. And therefore, under every equivalence relation, we can determine the equivalence classes of every element of that set. For example, uh, we observe that if a real is an equivalence relation on X, when X is the element of X, then equivalence class of X is what? X bar is equal to set of Y belongs to X, such that Y is related to X. That is, the elements which are related to X belongs to X bar. So when we can find equivalence class, so if the relation is equivalence relation on some set, and if the element is the element of that set, then we can find the equivalence class of that element. So when we can find equivalence class, if there is a equivalence relation on some set, and if we take any element of that set, then we can find its equivalence class. So how many equivalence classes we have under any equivalence relation? We have the equivalence classes under the equivalence relation is equal to what? The number of elements in that set. So we can find equivalence class of every element of the set of the set that on which the equivalence relation is defined. So we can find here is this is the definition of equivalence class. So when we find the equivalence classes, if the relation is equivalence relation, and we know that this Wiggle relation is an equivalence relation on Z. So we can find the equivalence class of every element of Z. So Z contains how many elements? Z contains infinitely many elements. What is Z? Z is set of element 0, 1, -1, 2, -2, 3, -3, and all the remaining elements. So Z contains infinitely elements, and therefore we have infinitely equivalence classes under the equivalence relation. That equivalence relation is what? Congruence relation. And the equivalence relation is a congruence relation, then the equivalence classes under that relation are called residue classes or congruent classes. So we can find the equivalence class under the congruence relation, but we call it as congruence class or a residue class. So A is the element of Z, and we can find the equivalence. This is the notation for equivalence relation, that A bar, X bar. Okay, so equivalence class of A bar is what? Is the element from Z. Again, the is X belongs to X. So here is Y belongs to X, because Wiggle is the relation on set X. Here is the equivalence relation is what? Congruence relation. So is the set from the same set, is the set of elements from the same set, that is X belongs to Z, such that X is related to A. That is, the elements of Z which are related to A belongs to A bar. What is A bar? A bar is the set of elements from the set Z that are related to A. X is related to A. So how can write X is related to A? So here is the Wiggle notation for general equivalence relation, but here the notation for equivalence relation is these three lines, that is congruence relation. So what is A bar? A bar is the set of elements from Z, that is X belongs to Z, such that X is related to A, that is X is congruent to A module N, and this set is called congruent class module N or residue class of A module N. This is what? Congruence class of A module N, or is called a residue class of element A module N. So this is the set of X belongs to Z, such that X is congruent to A module N. X are related to, those X are related to A belongs to A bar. So what is the X bar? X bar contains the set of, is the set of Y from X, that is the set of elements from X, capital X, such that Y is related to X, that is the elements which are related to X, which are related to this X, are is the element of X bar. All are the elements of X bar. So this is the definition of congruence class or residue class. Okay. So we simplify this residue class. So A bar is X belongs to Z such that X is congruent to A modulo N. So X is congruent to A modulo N implies what? N divides to X minus A. This is the definition of congruence relation. When A is congruent to B modulo N, if N divides to A minus B. So what is when X is congruent to A modulo N implies N divides to X minus A. And N divides to X minus A means X minus A expressed in the form N into some integer for Z belongs to Z by using definition of divisibility. And therefore X is what? A plus NZ such that Z belongs to Z. So this is the simplification of this definition of residue class. This A bar in this form and this A bar in this form both are same. This is the simplification of this equivalence class or residue class. So to justify the definition, we will find some equivalence classes under this congruence relation, and we find residue classes under this relation. So take N as 5, for suppose N as 5. We take N as 5. In order to understand this definition of a residue class or congruence class, for example, we take N is equal to 5. Then we have the different residue class module 5. What are that? So 5 means what? X is congruent to A module 5. We have to find the elements X belongs to Z such that X is congruent to A modulo N. What is A bar then? Now to justify the definition, we'll find 0 bar. Suppose first we'll find 0 bar. So what is the definition? By using definition, what is 0 bar? Is X belongs to Z such that X is equal to A is 0 plus 5, N is 5. Z, what is Z? Z is the element from Z. Okay. So what are the what are the values of Z? These are the values of Z. So from -3, -2, -1, 0, 1, 2, 3. If we substitute -3 here, Z as -3, then we have the element -15. So we have the element. If we substitute Z as -4, then we have here -20. So dash, 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 comma, -15 is the first element of this 0 bar. Then substitute Z as the value of small z as -2. So we have -10 answer. Then substitute z as -1, we have answer -5. Then substitute small z as 0, we have answer 0. In this way, substitute the z as 1, 2, 3, we have these elements. And this is what? 0 bar. So what is 1 bar? Then what is 1 bar? Then 1 bar is, this is 0 bar. Then 1 bar is what? Is again by using this definition, is X belongs to Z such that X is equal to 1 plus NZ. N is 5. So X is equal to 1 plus 5Z. Substitute Z from this set, capital Z. This small z, substitute small z as -3, -2, -1. So if we substitute -3, we have answer -14. Then if we substitute -2, then -2 means -10 plus 1 -9. In this way, substitute the answer, the values of z, small z as -1, 0, 1, 2, 3. We have this set. So this is 1 bar. Similarly, find 2 bar by using this definition. Substitute n as 5 and a as 2. So we have these 2 bar. This is 2 bar. This is 3 bar. That -12, -7, -2, 3. Then this is 4 bar. This is 5 bar. And if you observe 5 bar, then 5 bar and 0 bar both are same. Observe this, -10. Then the previous element is -15. The -5, 0, 5, 10, 15, all this. This is 5 bar is 0 bar. If you find similarly, if you find 6 bar, then it is equal to 1 bar. 6 bar becomes 1 bar. If you find 6 bar by using this definition, by using this process, then we have its answer is 1 bar, same to 1 bar. Similarly, 7 bar is 2 bar. 8 bar, if you find 8 bar, it is equal to 3 bar, like this. Then if you find a 9 bar, then it is equal to 4 bar. If you find 10 bar, then it is 0 bar. Again, 11 bar is 1 bar, 12 bar is 2 bar. In this way, if you find 46 bar, then it is 1 bar. So if you find 100 bar, then it is 0 bar. If you find 62 bar, then it is 2 bar. 68 bar is 3 bar. As so, what is the formula behind this? How we can write 68? 68 bar as a 3 bar. As if we divide 68 by 5, because we have to find where n is 5. So if we divide 65 by 5, then 13 is the question and 3 is the remainder. And that's why 68 bar is 3 bar. What is 657 bar? It's 2 bar. Why? Because if you divide 657 by 5, use calculator. If you divide 657 by 5, then answer is 131 point something. So this is division algorithm theorem. So 131 point something. Ignore the points, and then 131 is the question, and then 657 minus 5 into 131. The answer is 2. So how we can find these numbers 131 and 2? If we divide this 657 by using calculator by 5, then we have the answer 131 point something. So 131 is the question, and then 657 minus 5 into 131, this is the 2. And so 657 is what? It's 2 bar. So in this if n is 5, then these answers. If n is 5, then 5 bar is 0 bar, and 6 bar is 1 bar, 7 bar is 2 bar, 8 bar is 3 bar, and like that. 11, what is, why 11 bar is 1 bar? If we divide 11 by 5, then what is the question? Question is why 11 bar is question is 2. If we divide 11 by 5, then question is 2, and 1 is the remainder. If we divide 12 by 5, then 2 is the question and 2 is the remainder. If we divide 46 by 5, then what is the question? 9 is the question and 1 is the remainder. 9 5s are 45. Okay, so 9 is the question and 1 is the remainder, and that's why 46 bar is 1 bar. So why 100 bar is 0 bar? If you divide 100 by 5, then what is the question? Question is 20. 25 is at 100 and the remainder is 0. So 100 bar is 0 bar. If you divide 62 by 5, then what is the remainder? Remainder is what? Is 2, because 12 is the question. If we divide 62 by 5, then 12 is the question and 2 is the remainder. Like that, 68 and 6 5 is 7 bar, 68 bar. Okay, 68 bar is 3 bar, because 68, if we divide 68 by 5, then 13 is the question and 3 is the remainder. So what is the general formula to obtain this? That is the formula. What is the formula? That is, we have to find the remainder. Okay. So what is the formula? How we can find 68 bar if n is 5? Divide 68 by 5 and find question and remainder. Only find remainder. Okay, so 3 is the remainder. So if n is 5, then we have to divide the number by 5 and we have to find the remainder. But if n is 4, then you divide by 4 and find remainder. If n is 3, then divide by 3 and find remainder. Okay, so next is the question theorem. There are precisely or exactly n distinct residue class moduli n. So what do I have to prove? There are precisely or exactly n residue class moduli n. If we are observe here, then what is our observation? If n is 5, then we have only 5 distinct residue classes. What are that? 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. Only these are the 5 distinct residue classes. And all the remaining 5 bar is 0 bar, 6 bar is 1 bar. That is, we have only 5 distinct residue classes. What are that? 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. If n is 5. That is, if n is 4, then we have only 4 residue classes. What are that? 0 bar, 1 bar, 2 bar, 3 bar. Distinct residue classes. And 4 bar and 3 bar. If n is 4, then we have the only 4 distinct residue classes. What are that? 0 bar, 1 bar, 2 bar, 3 bar. If n is 3, then we have only 3 residue classes, 0 bar, 1 bar, and 2 bar, in this way. Okay, if n is suppose 8, then we have 8 residue classes. What are that? 0 bar to 7 bar. So if n is 5, then we have only 5 residue classes up to 0 bar to 4 bar. So in this way, there are precisely n distinct residue classes module n, and obviously what are that? 0 bar, 1 bar, 2 bar, 3 bar, up to n minus 1 bar. These are what? The n distinct residue class module n. That is, if we take n is 5, we have the 5 residue classes. If we take n is, as say, 6, we have 6 residue classes. Like that, if n is n, then we have n residue classes. What are that? 0 bar, 1 bar, 2 bar, 3 bar, up to n minus 1. We have to show this, that there are precisely, means exactly, n residue, distinct residue classes module n. So we will find first residue classes under module n. So take A as any element from J. So how we can show there are n residue classes module n? That is, if we find, how we can justify the statement here, that we have find, if we find any equivalence class of a residue class of any integer, then it is one of the residue class 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. That is, if you find 9 bar, then it is 4 bar. If you find 6, 5, 7 bar, then it is 2 bar. The answer of any residue class is out of the 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. If you find how many residue classes we will find under module 5, we will find infinitely many residue classes under module 5. How many equivalence classes are under module 5? That is, we can find equivalence class or residue class of every integer. So there are infinitely many integers, so we have infinitely many residue classes module 5. But distinct are only 5, that are 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. You find a residue class of 100. If you find residue class of 100 under module 5, then it is 0 bar. If you find a residue class of suppose 46, then it is 1 bar. That is, if you find a residue class of any integer, any element of Z, then it is out of this 5 residue class. So we have to write the same proof here. That is, if we find any residue class of any integer, then it is one of these residue classes, 0 bar, 1 bar, 2 bar, up to n minus 1 bar. How we can show there are precisely or exactly n residue class module n, module 5? By using this example, we prove that there are 5 residue classes module 5. What are that? 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. If you find residue class of any integer, any element from Z, then it is out of these 5. Then it is one of the out of these 5. Okay. If you find a 68 bar, then it is 3 bar. It is out of these 5 residue classes. If you find any, so here we give the same proof that how we can show that there are n residue classes module n. If you find a residue class of any integer, any element from Z, then it is out of these n residue classes. Okay, so let A belongs to Z be arbitrary integer, any element, and now we have to find the residue class of this A, and we have to show it is one of the residue class 0 bar, 1 bar, 2 bar, 3 bar, up dash n minus 1 bar. So let A belongs to Z be arbitrary integer. Applying division algorithm to A and n, that is, divide A by n. We have some quotient, we have some remainder. Suppose Q is the quotient and R is the remainder. We have unit Q and R belongs to Z, such that A is equal to NQ plus R. Obviously, this remainder is what? Strictly less than divisor and greater than or equal to 0. This is the division algorithm. That is, apply the division algorithm to A and n. We have two integers Q and R, such that A is equal to NQ plus R. That is, divide A by n. We have Q is the quotient and R is the remainder. So R is strictly less than n and greater than or equal to 0. Remainder is always greater than or equal to 0 and strictly less than divisor. And then A minus R is NQ, and this implies n divides to A minus R, because A minus R expressed as n into some integer. So n divides to a minus r, and means a is congruent to r modulo n. And we know that if the two elements are congruent, then their equivalence class are same. If the two elements are congruent, then x is congruent. If x is related to y, then x belongs to y bar. And if x belongs to y bar, then x bar and y bar both are same. So here a is congruent to r modulo n, means a is related to r. Therefore, a belongs to r bar. A belongs to equivalence class of this by using this theorem. X is related to y, then x belongs to y bar. So this is the theorem of chapter number 1. So a is congruent, a is related to r, therefore a belongs to r bar. And a belongs to r bar by using this theorem, a bar is equal to r bar. That is, x belongs to y bar, if and only if x bar is equal to y bar. A bar is equal to r bar. But r is what? R is running from 0 to n, 0 to up to n. Okay. So r is, the value of r is what? 0, 1, 2, 3 up to n minus 1 bar. N minus 1 up to n, no, strictly less than n means up to n minus 1. The value of r is what? 0, 1, 2, 3 up to n minus 1. And hence a bar is what? Is either 0 bar or 1 bar or 2 bar or n minus 1 bar. That is, hence residue class of any integer is one of the, this a is any integer, any element of z. And so if you find equivalence class of residue class of any integer, any element of z, then it is one of the residue class 0 bar, 1 bar, 2 bar, 3 bar up to n minus 1 bar. And that is, there are at most n residue classes modulo n, namely this. So there are at most, now we have to show these all are distinct. Then if all these are distinct, then we say that there are exactly or precisely n residue classes. So here is the sentence: there are at most n residue classes modulo n, namely these 0 bar, 1 bar, 2 bar up to n minus 1 bar. So now we have to show these are distinct. We have to show these all are distinct. So the proof is by contradiction method. We assume that the out of these n residue classes 2 are same. Suppose I bar is equal to j bar. Obviously I and j are running from 0 to n minus 1. And then we have these two equivalence classes are same, means the elements I and j are related. I is congruent to j modulo n, implies n, the two equivalence classes are same, means the two elements are related. Two elements are related. And then by using these theorems, these are if and only if type theorem. Then n divides to I minus j. I is congruent to j modulo n, implies n divides to I minus j. And but I minus j, what is the I minus j? I and j both are strictly less than n, means I minus j is strictly less than n. And this means and n divides to I minus j, which implies I minus j is equal to 0. Because if when the larger number divides to smaller number, then the smaller number must be 0. So I minus j is equal to 0, because n is larger than I minus j. Therefore I minus j is 0, and therefore I is equal to j. That is the two equivalence classes. If I bar and j bar are same, then I and j are same. That is these 0 bar, 1 bar, n minus 1 bar all are distinct. If we take the two equivalence classes same, then the elements are I and j are same. Means these 0 bar, 1 bar, n minus 1 bar are all distinct, and hence we say that there are precisely or exactly n residue classes modulo n. And what are that? 0 bar, 1 bar, 2 bar, 3 bar up to n minus 1 bar. So the set of all these residue classes is denoted by the notation Zn. The set of all residue classes is denoted by this notation Zn. So we'll see the remaining topic the next lecture.